Let us consider the Doppler effect for sound. Imagine that I stand here and I yell. I'm going to emit some frequency. And what's going to happen is the waves are going to spread out concentrically around me. The wavelength will be the same in all directions. And what we have is an observer who stands anywhere relative to me is going to hear some frequency f, which is going to be related to the emitted frequency f naught. And they will be exactly the same because we have no relative motion between the two observers. However, if I now run toward the observer at some velocity v, emitting the same frequency f naught, we're going to find that the waves in front of me are going to pile up, resulting in a shorter wavelength. And we're going to find behind me the wavelength is going to spread out, and we have a longer wavelength. And this will be related to the emitted frequency because we know the wave equation tells us that the speed of sound, which is a constant, is equal to lambda naught f naught. The observer, also governed by the wave equation, is going to hear some frequency f. However, because the speed of sound is a constant, that's going to be equal to lambda f. And because we saw that lambda in the direction of travel is going to be less than lambda naught, that means that the frequency must be greater than the emitted frequency. And this is the Doppler effect. And so the equation that we'll use in order to calculate the Doppler effect is we're going to take the frequency that is emitted, f naught, and we're going to relate that to the frequency that's observed, f. And it's going to be multiplied by some factor, and the factor is going to be the speed of sound plus the speed of the receiver divided by the speed of sound plus the speed of the emitter. And in order to have everything work out, we have two conventions, and that is the speed of the receiver is positive when it moves toward the emitter, and the speed of the emitter is positive if it moves away.